climate change, the challenge of the century. As we know, there is an urgent need to find solutions towards more sustainability. One of them is the storage of the surplus energy produced by the renewable sources. In this respect, our team at the University of Bern in Switzerland, which is part of a large collaborative European project called RECYCALYSE, is focusing on water splitting or water electrolysis. To make the reaction economically relevant, catalyst development still requires improvements, especially the one for the anodic side, meaning for the oxygen evolution reaction or OER. In this respect, I developed 4 catalysts, iridium and iridium-ruthenium nanoparticles that were deposited either on carbon cation black or on commercial antimony doped tin oxide, ATO. The synthesis of the nanoparticles was performed following a surfactant-free colloidal route using a low boiling point solvent. The mean particle size was determined by TM, and independently from the support or the material, a size of about 1.5 nanometer was obtained. After depositing the catalyst on a carbon-based gas diffusion layer, GDL, by vacuum filtration, EDX mapping was conducted to first calculate the ratio between iridium and ruthenium, which was respectively 40 to 60. With this technique, we can also clearly see how the electrode is built. We see the carbon fibers and the microporous layer, the MPL of the GDL, and the catalyst layer on top of it, forming this brighter layer. We can also see that the catalyst is forming a homogeneous layer and that it does not penetrate through the GDL. With those electrodes, I investigated the performance of the catalyst in the electrochemical flow cell that you can see here. The performance was first tested in terms of activity by stepping at different current every 5 minutes at 3 different temperatures, 30, 40, and 60 degrees. On those plots where the potential is plotted against the current density, we can see that for all 4 catalysts, the increase of the temperature improves the activity of the catalyst. And by comparing the different composition or the different support, we see that independently from the support, adding ruthenium to the catalyst improves its activity, and that independently from of the material, carbon support shows higher activity at low current densities. Testing the performance of the catalyst implies to test its stability as well. Using the same cell configuration, I perform a stressing experiment at 60 degrees by applying 1.6 volt for 2 hours. From this plot where the normalized current density is against the time, we can extract 3 main points. First, the catalyst on the carbon support, the black curve, shows a higher slope, meaning a higher degradation rate. Second, we see that iridium on ATO, the red curve, is in line with the unsupported iridium catalyst, the green curve, meaning that ATO itself is not causing further degradation. And finally, by comparing the red curve with the blue curve, which is iridium ruthenium on ATO, we see that adding ruthenium to the iridium catalyst, it does not affect the stability of the catalyst. And with that, I come already to the end of my poster presentation. I just want to add that further experiment will be conducted to better understand the implication of the GDL in the degradation process. And therefore, we are going to use another substrate, which will be a titanium-based porous thin layer or PTL. I would like to thank you all for watching my presentation. See you soon.